right, Dr. Jocelyn Bell is back. You were just here in March.
February, I think.
March. And loved it so much he came back to talk about companions of neutron stars.
All right.
All right.
I'm a friend of them too.
So without further ado, Shield.
Well, thanks very much for having me back. Yeah, I was excited to hear that you were okay with me coming back.
We're going to get you in the regular rotation.
Yeah, and so last time I talked about a completely different subject. So I suggested that I talk about something that's actually quite closely related to my research that has been ongoing for the last 5-6 years now, talking about companions of neutron stars and in particular companions of pulsars. And since it grew out of my thesis research, there's been a steady stream of acknowledgments that I've had to start putting on this. It's almost connected all the way around to all the different places that I've gotten data from or used data from. And this is my current affiliation right now. City University of New York at the LaGuardia Community College campus, where I teach astronomy and astrobiology, and the research home I have is at the American Museum of Natural History, where I was earlier today doing some project work. And so I'd like to start off with the discovery of pulsars. Anyone know who this is?
Jocelyn Bell.
Good. Jocelyn Bell, the discoverer of pulsars. It is the proper discoverer. I can show you her discovery. This is actually her handwriting. Discovering, using a radio telescope, figuring out precisely where these things are located. 19 hours, 20 minutes. First observation, 28th November 1967.
Wow. So she didn't know, there was no name called a pulsar yet. She called it pulses.
Didn't know what it was. This is it right here. Right? So this is the radio signal, and she identified the peaks down here and tried to identify about how many seconds apart each of these pulses were.
Pulsar.
No idea what they were.
The name Pulsar came from a journalist, actually.
Yeah, that's right. That's right. And it was a great mystery, although it had been proposed before this observation was made, and the publication that then came out by Hewlish, her advisor, who went on to win the Nobel Prize, and somewhat controversially she did not, but we won't get into that right now. That there were these things that could be out there that were about approximately this size physically in space, but were massive like the sun, let's say. You just squash those things down, and this is kind of what you expect them to look like. And the whole story had already been worked out. Actually, one of the first people to work it out was Fritz Zwicky, who was interested in supernova. Right? So the story sort of goes like this. You've got this giant star. The core of this giant star is fighting this battle against gravity, pulling it down by providing a lot of energy through fusion. But eventually, that sort of thing runs out. You don't get any energy out anymore when you hit a very particular nuclei. And you end up with an implosion of the core, which bounces off, causes the rest of it to explode. But the implosion of the core can bring you down to densities that are strong enough, high enough, that you end up with this remnant. This was the calculation that was done. It was based off of calculations previously done by Chandrasekhar explaining white dwarfs. So there's all this explanation of how you can get these really weird, very dense objects that were identified as the companions of Sirius and Procyon, among others. And this was all explained by something called electron degeneracy, electrons that refuse to get close to each other. And then it was realized that there were these nuclei that also had this kind of characteristic, and you should also have stars that kind of behave like that, and that's where these neutron stars would have come from. And the explanation for these pulses then looks something like this. So when you form one of these neutron stars, they collapse down sort of dramatically here. Here's that little ball that's the size of New York City, its physical extent at least. You also end up with magnetic fields that are about the equivalent of 10 million MRI machines. Kind of excitingly strong magnetic fields. These things are going to be rotating due to the conservation of angular momentum fairly quickly. Actually pretty close to the breakup speed if you calculate how fast they're going. If you trace out their rotation rate somewhere out around probably where this box is, that the rotation rate of the pulsar would be actually that the speed would be the speed of light. About there. They call that the light cylinder for a pulsar. These things are made out of charged particles. The charged particles are accelerated quite a bit, tremendous forces, magnetic fields. These things get shot out and do all kinds of fun things. And you end up with radiation that gets spewed out because of this sort of gigantic magnetic field. That radiation is going to take many forms, among of which would be radios. And radio waves are what were picked up by Jocelyn Bell in 1967. And that's what we continue to call pulsars to this day. We now know thousands of them. Quite exciting.
Do they start out as radio waves?
In the sense of
Once they travel, they lose energy and they become.
No, they're formed. Well, it's interesting. They're formed actually quite far away from the pulsar. They're not formed here.
Okay.
Usually formed way out there, and the emission mechanisms are still a little opaque. We know that they are related to how much energy the pulsar has, but they're actually very low in energy compared to the amount of energy the pulsar is creating. So we don't exactly know why. I would say still exactly why the radio is in the form and shape it is, but it's formed as radio fairly near within the light cylinder of the pulsar.
Are there any where the axis of rotation and the magnetic axis coincide?
Well, we wouldn't know because if the magnetic axis might be associated with the radiation we see, and if they did coincide, we wouldn't see the pulses. So it'd be kind of hard to identify. And so in those situations, we just wouldn't know.
Okay.
All right, so I'd like to kind of move on from this sort of picture that I think most of you are aware of, because it's a famous story of pulsars, lots of people have been studying them, to kind of show you some additional mysteries that aren't as well advertised with respect to pulsars. These are mysteries that sort of first showed up in the 1980s and have continued to become more and more interesting to the 90s and even into today. So the first one I'd like you to look at is sort of a pulsar that was about the same as what Jocelyn Bell observed. And I'll see if we can get actually the sound. I don't know if we can, but we'll try. That's the wrong one. Let me try this one.
Oh dear.
I can't get the first one to go. There we go. So I've already given away the punchline, but that's okay. So this is just taking the radio form and turning it into the pulsation of a speaker, right? Just so that you get some sort of other auditory stimulation while you're listening. And this is about what Jocelyn Bell was observing, about a 1 second pulsar. That's a sort of a normal pulsar.
Well, you would think when you were hearing this from the first time from space, you would think this would be an alien.
That was one of the proposals. I think tongue-in-cheek, but that was one of the proposals.
Right.
So that was one.
Yeah, LG, that's right. Yeah. Little green men.
All right. But when these neutron stars are born, this is about the rate of pulsation that they have. Much faster, right? So if you were to observe the pulsar at the center of the Crab Nebula, for example, that's what it's doing. Right? A little bit slower than this, but this is about as fast as you can get. And you can do these calculations to figure out how fast a pulsar can get when it's born. In this table. And it's like that. That's coming out here. Try this.
It's like it almost went to sleep.
It's okay on mine.
Yeah.
Okay.
No, not okay. Try again. Alright, that's one.
Yeah.
Is that related to the angle between the axis of rotation and the magnetic axis?
The reason that you see a pulse is because there's an angle, and so it's a lighthouse effect, and it sweeps past you each time. You can also get interpulses. This one does not have interpulses, but this one actually does probably have an interpulse. There's like a secondary pulse halfway in between. That might be the other side coming around. So that's when the pulsar is born. That's how quickly they are seen to pulse or seen to rotate. It gives you a measurement of their rotation rate. But in 1982, pulsars were discovered that were rotating this quickly.
Wow.
So this is one rotation every few milliseconds, which is absurd because you actually can't get this from the scenario I was describing. You have a millisecond pulsar. It really doesn't like to do this, does it? Let's try one more time. I think it might be the combination of the data.
It's the Christmas lights.
The Christmas.
Little green light.
This doesn't want to come up, does it?
There we go.
There you go.
All right, let's go from there. So I'm going to try to explain to you where these millisecond pulsars came from. They don't come from the normal story that we have. So the scenario that you have to explain where millisecond pulsars come from is this. You've got a binary system. So you have one star that's a little bit larger than the other, and the larger star is going through its red giant phase and rapidly headed towards one of these supernova explosions, like that, right? This is artists' impressions of what this would look like. Of course, the supernova is so bright that you can't see the other star, right? They're both there, but you only see the one that explodes. And in many cases, they have kicks that occur, and that could disrupt the binary, but not always, especially if they're in very tight binaries. They won't necessarily be disrupted. And so after all is said and done and the dust settles, you end up with a scenario like this, where you have a rather large star, maybe one that's about headed to a red giant phase itself, and the leftover core remnant of a pulsar. So now this is what we would call a binary pulsar or binary neutron star. Any type of neutron star that's with a companion is a binary, and there's a whole range of them. You have binary pulsars that have different kinds of companions, and so that's the goal of what I'd like to describe to you today. And we'll start with the simplest one, which is the scenario I'm describing, where we've got this regular star, main sequence is what we call them, regular stars, orbiting in a dance around with a neutron star, like this. And eventually that giant star that's nearby gets bigger and bigger as it becomes a red giant. And if it gets large enough, the outer material, the outermost material, will experience more gravitational pull from the neutron star than it does to its own core. If that occurs, you end up with a system like this. And this has a special name when we observe these things. Does anyone know what these are called?
Accretion disk.
That's the accretion disk, but when I observe them, these are particular names for these objects. These are called Xray binaries whenever we see them, because these accretion disks here are colored in blue, but really they're colored in X-rays. And so they're extremely bright in X-rays. They're some of the first X-ray sources ever discovered. So I happened to go to the 50th anniversary of the first discovery of SCO-X1, which is the first X-ray binary ever discovered. And they are seen all over the sky, more or less. We have a huge catalog of these X-ray binaries. And this is the story. The story is you have to have a binary, and you have to have a compact object. Sometimes that compact object's a black hole, but sometimes it's a neutron star. And you can tell the difference, if you're careful, by looking at the light that's coming from the X-ray light. And in some cases, you can actually see the X-ray pulsations. And you have these X-ray pulsars. So you have these radio pulsars, and you can also get X-ray pulsars in these scenarios when you have this special situation where you form these accretion disks and extremely energetic scenarios. So what does this have to do with millisecond pulsars? Well, what ends up happening is that a lot of that material ends up falling down onto that neutron star, and that material is spinning as it falls down, and the conservation of angular momentum says it has to keep spinning as it falls down, so you end up spinning up your neutron star. And you can spin them up to very, very fast speeds, much faster than you can actually have them born in the first place.
That's what's creating the speed on the neutron star is the accretion.
That's what it is.
That's wild.
That's the explanation for how you get millisecond pulsars. The only one that I know of that makes any sense. There's other ones that have been proposed, but for the most part, this is the one that we have. The confusing thing is that we see maybe a quarter of these millisecond pulsars do not have companions. So 3/4 do, so you're kind of like, okay, that makes sense. And a quarter do not. So what happened to the companion? Well, you might get a hint of what might be happening to the companions in this drawing.
Just got eaten up.
It either gets eaten up or it gets destroyed in some fashion. Neutron stars have tremendous winds, tremendous energy that's being ejected out, and that can easily go through and kind of disrupt the companion. So when some of these were first discovered, they had this idea that the companion was being ablated by the neutron star, and the name for such a system was given Black Widow. The Black Widow pulsar was the name for it. Mistakenly, because I think actually black widows do not eat their mates, but this is the idea, right, is that the neutron star is somehow destroying its companion. Since then, this story has been a little bit, I don't think it's as clear that that's precisely what's going on, but it still is sort of one of the strongest pieces of evidence that we have, since we see so many that are in these sorts of companions, and we do see situations where it looks like the companion's losing mass. Yeah?
You mentioned earlier on that at the diameter of the neutron star itself, you're roughly at the breakpoint because of angular momentum, or because of the rate of spin. Right? So as you speed them up,
Yeah, you
especially
get
if you're
very,
speeding them
very
up by
close.
several orders of magnitude.
That's right.
What's happening to the material in the original star, in the original neutron star? Are you
The-
ablating material?
The material in the original neutron star stays in there. So you're close, but what basically happens is your light cylinder gets smaller and smaller until it almost hits where
Well, that's
the
the
neutron
light
star
cylinder.
is.
I was just thinking about the
Neutron star
the
itself.
neutron star itself, its ability to hold itself as you spin up.
It's got
It's
quite a
still
lot.
weights.
It's pretty
It's
hefty
still
gravity.
weights.
It's right before a black hole. My advisor, when I was writing doing my thesis, he gave a short little presentation once that said neutron stars can do everything a black hole does and more. and so assuming that they're like black holes is not quite right, but it's very close. And so it's essentially they can hold on to that stuff no problem.
So you're not going to get an angular momentum breakdown.
No, you don't. You can. There's only one way I know of to really destroy a neutron star, and we'll get to it.
So, given what Aaron has said, is there a size limit to how big a neutron star can be? Because clearly,
Yes.
if it's
There is. Yes, absolutely. So there's a maximum size for a neutron star.
when you're throwing a whole other star onto it, though.
So you're not throwing a whole other star onto it crucially, because what ends up happening as the material comes in is
You're shooting
actually
out
there's
stuff,
a
too.
lot of energy coming out, so you
Yeah.
end up with a standoff shock that prevents you from accreting more, which is why you don't see microsecond pulsars. You see millisecond pulsars, but there's nothing that goes faster than a millisecond. Yeah, so there is a limit, absolutely. But it's not a limit set by the material, it's really a limit set by the balance of the energy that's given off with the material that's coming in.
You said there's a lot of these around. I mean, how many would you think are in our galaxy?
How many, well, how many Xray binaries are in our galaxy? Is that the question? Or how many neutron stars?
Well, no, Xray binaries.
So the number of Xray binaries that are detected right now is in the hundreds.
Oh, that's all.
But there's certainly orders of magnitude more, because this is a strongly biased selection effect, right? We only have a few X-ray telescopes out there that can go look for them.
And these would be very old.
Ages are really hard to measure in X-ray binaries. And so unless you have a really good handle on what the accretion rate is and what you think the progenitor looked like, it's really hard to tell. I think there's a wide range of possible ages, and we actually have some of these that have been recently discovered that switch back and forth from being X-ray binaries to being regular pulsars, back and forth and back and forth, over the course of years. which might mean that they can have duty cycles, so-called lifetimes in these features that are on the order of human lifetimes. At least some of them do.
That'd be like
Some of them might be.
feeding, not feeding.
That's right.
So
And
highlight
sort of something like this,
Yeah.
where they stop, and then, I don't know, they sort of settle down a little bit, and then, or more material comes off the star, and then
Off
you
they
start
go
to
again.
appreciate it.
Yeah. God, that's weird.
They're very peculiar.
That's a
effects.
great kind of way to describe a neutron star, though. Is a black hole that just has so much more.
Yeah, it does. It's yeah. And so then he also had a talk that was white dwarfs are just like neutron stars, but they can do a lot more. So he
Keep going down that rabbit hole.
But yeah, so the question really then becomes, well, how do you find these things? Like, where do I? And then I would like to talk a little bit about my particular research, which really deals with systems like this, systems that have stopped being Xray binaries and have started being something else. And the way you discover these sorts of systems, and in particular discover millisecond pulsars, which were discovered first in 1982, and then there have been maybe a few dozen that were discovered up until about 10 years ago when the field really took off, and we really started, it was a golden age of discovering millisecond pulsars, thanks to this particular satellite. Long may she fly. The Fermi GammaRay Space Telescope, which is even still collecting data. It's a fantastically interesting telescope. I don't know if you can tell how you collect your light in such a thing, right? What's going on is your gamma rays come through here, and essentially it's a particle detector. Right? And so you end up detecting the interaction of the gamma rays with the material that's in your telescope that produces these pair productions within your telescope of positrons and electrons, and then you back out where it came from and how much energy it had, and that's how you detect the gamma ray. Fantastic thing. The reason this is another great reason to have a particle detector is that you can see a huge range of the sky, right? Because things that are coming in this way you can tell, and things that are coming this way, you don't have to just be looking in one particular direction. You get maybe a quarter of the sky in one fell swoop.
Right.
And this thing has been looking at stuff for almost 10 years now, and this is the latest Allsky map that they have done. So this is all the gamma rays for 10 years, looking about a quarter of the sky at a time or so. And I just love this map. It's absolutely fantastic. So the Milky Way is unmistakable, but there's also all kinds of other really strange sort of loops that you're seeing in here that are mostly due to old associations, supernova remnants, things of that nature. Another thing that you might be able to see, I can just barely see it, are these sorts of figure eights right around the center. Anyone know what those are called? They have a special name. Those are the Fermi Bubbles. The Fermi Bubbles are the evidence that 6 million to 10 million years ago, somewhere around there, our Milky Way was a quasar. An active galactic nuclei.
That recently.
That recently.
That's amazing.
And that's been seen in the Fermi data as well. But the stuff I'm interested in, I don't study that, even though I think it's fantastic. It goes again.
It's mind-boggling.
Yeah.
It's mind-boggling.
What,
Say that
we
again.
are-
That galaxy was a quasar only 6 million years ago. Billion or million?
6 million.
Million?
That's
Million. That's
Wow.
baby stuff.
Yeah, that's
That's
like
right.
yesterday.
Speak for yourself, young man.
That's,
That's a tough room.
that's good.
Just no respect. Such little respect for his elders.
Maybe because of so much data.
So those bubbles are centered on the galactic center then, or?
Yeah.
Okay. Yeah, these bubbles are centered on the galactic center. Exactly. And there's other evidence, too, that this is what had occurred.
Did Fermi propose this?
No, this was
No,
discovered
exactly.
completely serendipitously.
Well, so they gave that the Fermi bubbles as a
Fermi bubbles because they were detected by
by,
Fermi,
by the camera.
but no one expected to see them.
Yes.
That's the best kind of science.
I'm really interested, though, in all these little pockmarks. About, say, 2/3 of those pockmarks are distant blazars, the centers of very distant galaxies where the accretion rate is very high in the supermassive black hole, and there's a jet pointed towards us, and we're looking right down that jet at these gamma rays shot in our direction. But the other third of these are pulsars. a third of them are neutron stars that are forming gamma rays and are actually pointing us in the direction of where to look. And it turns out that a lot of the systems that I'm interested in are rather bright in gamma rays. I think it's the data. It just doesn't like the data.
Strange.
And so after you find these points on the sky that you think they might be for various reasons, pulsars, you point your radio telescopes. This is a picture I took of Parkes radio telescope when I went down there. It's a beautiful place to go. It's in Australia. It's about 5 hour drive northwest of Sydney. And then this was a telescope that I used to do most of my thesis work. So this is on Kitt Peak in Arizona. This is the so-called MDM telescope, which used to stand for Michigan, Dartmouth, MIT, but now neither, I guess Michigan and Dartmouth are still in the consortium, but MIT is out and Columbia is in, but they didn't rename it. So this is the 2.5 meter telescope at MDM. They say it's the smallest 4 meter telescope in the world because we got very great skies. Excellent seeing there on the southwest ridge there. And this is the control room that I spent many, many nights, including I think one Christmas and definitely one election day in. Just staring at these objects where Fermi was basically telling us to look. And Parkes had also discovered in some cases, although that's southern hemisphere. In the northern hemisphere, we use Jodrell Bank telescope, which is where Jocelyn Bell worked. And here's some of the data that I was working on. This is some 20th magnitude object here, but it's kind of nice to see it blink in and out. Wow. So what I'm looking at here is not a pulsar. This is actually the companion to a pulsar. And it's sort of an interesting question. Why do we see it blinking? This is over the course of maybe about 4 hours or so, blinking in and out like this. And the reason that we see this is because this is what's going on. So at this point, basically you don't have a Xray binary anymore. You no longer have the material coming down onto the neutron star, but you still have this distorted star that's orbiting around. And in particular, it's being heated by the neutron star. Then as you see this thing go around, you'll see the bright side and you'll see the dark side, which means you'll see a bright and a dark and a bright and a dark. So what I'm seeing is the orbital period around.
Is that tidally locked?
They're definitely tidally locked. All of them are. So these are the things that I'm interested in. I call them short period binary millisecond pulsars. That's kind of what I'm interested in. And then people further categorize them in different ways. Black widow pulsars are another name for these things, as I mentioned before. And now there's a whole other category of them with slightly different companions that because they started with spiders, they've now continued with spiders, and I call them redbacks, which are spiders from Australia because they were discovered by Parkes. All sorts of fun things. I sometimes call them zombie pulsars because what's happened is that these pulsars have been recycled. They started off slow and they have been spun up, and as they spin up, they end up expelling a lot more energy. They become much brighter in the sky, and so they've sort of been given a new life, as it were, after.
These are off the plane? These are where are they? In the halo? Or are they?
These are all what we would call field. Finding them in the plane is difficult. Not impossible, but hard. You have to get very, very precise pointings to be able to do that. But I'd like to mention, as we go on, some other possible companions, and actually most of these occur in sort of similar scenarios. Where do you get these other companions from pulsars? This is basically the same story. But after you have something like an accretion disk and some disruption of the companion, out of the accretion disk you can get all kinds of interesting things showing up. So these are some of the more famous ones. These are the 3 pulsar planets that were first discovered. Really? They're actually the first planets that were discovered outside of the solar system, and they have names. The IAU has now given us these names. Draugr, Poltergeist, and Phibitor are the names of the 3 pulsar planets that were discovered in 1992, 1994, believe it or not. Well before the Nobel Prize winning 51 Pegasi b. So
So is the assumption these were formed from the accretion disk after the neutron
That's
stars?
right. So they're
Hence
formed
their
from
ghostly names. I got it.
right. That's right. So yeah, everything is zombies and ghosts with pulsars. But they'd also be really weird worlds to think about. You know, you're here, you're orbiting basically a pulsar. Maybe there's some extra gas material from the accretion disk out of which you were born. But all of your energy is basically coming in the form of X-rays and gamma rays. You might be in like a habitable zone around the neutron star, but it's a weird sort of habitable zone, right? Because you're not receiving black body radiation, right? You're not receiving the sort of visible light that we would all expect that we would like to have, right? You're receiving X-rays, hard X-rays, and gamma rays. Maybe if you had an atmosphere, you could reprocess that somehow, but these things are tiny little planets. Dragor is the size of our moon. It's the smallest exoplanet ever discovered. So it's sort of an interesting thing to imagine what you might experience being on one of these worlds. But yeah, formed out of the same sort of systems that I've been interested in as well.
It can't be easy to detect that.
Well, you'd think not, but it turns out
Moon.
turns out that when you have a millisecond pulsar, you have an amazing clock. And as you move that clock around, you can really easily measure those motions. And so it's the measurement of the motions of that clock. You can see tiny little variations in it that allow you to detect those. There's no chance that we're ever going to see this directly, right? This is just...
But even still, the gravitational force of the star next to the gravitational force of that thing.
Right, but it's
You can't move
still
it a
enough,
lot.
because when you're talking about a millisecond, it's enough for the orbit, you know, there's a tiny little variation in that orbit, and you definitely can see it.
Wow.
You can see it only in the radio can you see these sorts of things, but they're definitely there. This is how we detect pulsars as binaries. It's actually one of the reasons it's hard to detect millisecond pulsars in the first place, because the pulses don't line up, right? They're not regular, because as the orbit's happening, they're being Doppler shifted, and there's another effect called the Shapiro delay that causes the pulses to get farther apart and narrow together. And if you think about how you were going to find a pulsar, you want to line up all those pulses together to get the strongest signal. And if you don't know what the binary period is, it's kind of hard to do. It's a hard game to find it, but when you do, you get all of this information for free. You get what the companion is. You don't quite get what the mass of the companion is. You get something called the binary function, which tells you something about if you knew what the inclination was and precisely what the mass of the pulsar is, then you would know the mass of the companion. But you know everything else. This is another fantastic one. It was discovered in 2011. Another pulsar planet, but this one is so close to the pulsar and of such a mass, at least if we take the best estimates for what the inclination probably is, that if you work it out, you find that the density of this thing has to be so high that the only possible explanation is that it's made out of diamond. It's the only material that makes enough sense. So the idea is that you have some sort of star that has been kind of constantly had all of the outer material pulled off. You end up with the core. The cores of many of these stars are carbon and oxygen, and so if you take the lightest stuff that it would be carbon, you'd end up with a diamond, the largest diamond in the universe, as they sometimes say. I don't know, universe is right, but maybe our galaxy.
Okay, now hang on. Let me process that. The planet is that? Or
That's right. The planet is a diamond. Right. So this is a planet that's approximately the mass of Jupiter, but it's 100% carbon.
What is the mass of Jupiter in carats?
That's a great question. And I think someone quoted this once, but it gets absurd after a while, so I'm not going to. You can go look it up if you'd like. Also, this is not quite. I'd say it's pretty certain that they've seen something like this, but I'm going to withhold judgment. This is the best explanation I've seen as to what this particular object is, but they could be wrong. It could also just be a regular star if they messed up something with the way that the density had to be. But the best fit density estimate is that this is the core of something that used to be like a white dwarf, but now it has become so rearranged that it ends up as a diamond. essentially. And then these, if you have a very large star that also explodes and forms yet another neutron star, you end up with a double neutron star. Now, a number of double neutron stars have been discovered, including one double pulsar, where you actually measure both pulsars. But this particular object, 1913 plus 16, is known as the Hulse-Taylor pulsar, which was the first pulsar that was detected to have a neutron star companion. And after monitoring it for about a year, they noticed that the orbit was changing. And the only explanation they could come up with for how the orbit was changing, how the orbit was getting tighter and tighter, was that it was losing energy to gravitational waves, for which they won the Nobel Prize in the 1970s. Discovering indirect evidence for gravitational waves. Of course, now we have direct evidence for gravitational waves and other Nobel Prizes related to that. But this is another possibility for companions to neutron stars and companions to pulsars. What's interesting about thinking about these things is that if they're losing energy to gravitational waves, they're coming in closer and closer. Eventually, what's going to happen is this, which is the way I know of how to destroy a neutron star. So this was gravitational wave event in 2017 on August 17th, something I mentioned the last time I was here. Fantastic event, right? We saw the gravitational wave and we saw the electromagnetic counterpart to it. Distant double neutron star in a completely different galaxy. But the signal was such that we could constrain all sorts of interesting things about how reality behaves. And so this is where I'd like to leave our talk, our sort of exploration through the different companions of neutron stars.
Now, how far was this?
How far away was this? This was about 1 billion light years, give or take. I don't remember the quite.
Some feet to detect that.
Yeah, well, fortunately, you're giving off in this sort of situation something like the mass of the sun in energy in a second, right? So, yeah, it's pretty easy. It's supernova quality at that.
And after this happens, there's nothing left, and nothing physical left?
So this is actually an interesting question. Probably black hole is the answer to this, although these were destroyed. But in general, I think it depends on exactly how this occurs or something like that. So if you get a remnant, it's going to be a black hole. It's not likely to be a neutron star, but they can completely disrupt it if they explode. And in this situation, it liberated enough material that I don't think they expected.
So what happens then? Could it be pulled apart to where the nuclear degeneracy no longer? I mean, does it?
Well, in fact, this is what occurs.
Is that
Right? What happens is this material that's coming off, it ends up being the seeds for very heavy nuclei, like all the gold in my ring. And that's where they come from. If you do the census, you end up with all the nuclei being formed out of this sort of event. Here they are sitting degenerate in a neutron star for, who knows, maybe millions of years. I don't really know. It depends on how long it takes for this whole process to go. And then in an instant, all of that stuff is spread out for us to go mine later on.
1 billion light years away.
Well, that's in their galaxy. It happened here too. It happened in our galaxy. It just didn't happen yesterday.
Luckily, not near us.
Well, it had to happen somewhat close to us, otherwise it wouldn't be here. We would.
Oh, yeah.
But to follow on Mike's question, how do we know what's left at the end? I guess.
The only real way you can do that is by judging from the gravitational waves. I'm not a gravitational wave astronomer, so I don't know much about how this is precisely done, but they can figure out how large the final object was from the gravitational wave signature. So at that point, then you know, and you know sort of what the range of possibilities for something that's of that mass can possibly be. And then you say, okay, it's got to be this or that.
But I don't know how to have. I mean, this neutron star is a nucleus basically, right?
Sure, you could think of it that way.
So if you're going to split this apart, all of a sudden you've got something that's probably not stable somehow because it doesn't have the mass if it's coming off. And so what happens with that?
So what I think of it as this, as these things collide, they're spewing out this material.
Yeah.
when you look at the models that people have for neutron stars, right, in the interior it's a big mystery. It's this weird mixture of whatever nucleus stuff that I don't understand. But as you get closer and closer to the edge, the crust, you start to see sort of normal matter kind of show up. And there's interactions between things like iron and nickel nuclei that form right at the very outside. There's even a tiny little atmosphere on neutron stars. The dynamics is just absurd, right? Like mountain on a neutron star is a millimeter or something like that. It's just a nonsensical thing to think about, but it does. You do have this gradation from normal matter into this neutronium, if you want to call it that. So this is it. This is what I wanted to show you. I wanted to show you some.
Thank you.
Happy to take questions.
There'll be a quiz tomorrow.
We asked a lot of our questions here.
So the image you had earlier, where you said there's not much visible light, is there actually enough visible light to illuminate like the planets that that were discovered, or is this more of a
Here?
Yeah.
There would certainly be enough visible light. Okay, so that's a good question. Could you see by it?
Yeah. So is this realistic?
Your Mac's about ready to turn off, by the way.
Oh, low battery.
Yeah.
Low battery.
That's why.
I think I'd have to look into that. I'm not sure. I don't think I've
Would
looked
you
very
see
carefully.
Would you see that?
The other thing that you have to realize is that in this artist's conception, at the very least, there is the idea that the surrounding material is steered there, which would be fluorescing as well, because it's in a really highly energetic environment. So you could get some ambient light from that. And in that case, that's really what so if it was just the neutron star, I think you would still get enough light. For example, the crab is visible. The crab pulsar is actually visible with really.
These are tens of millions of degrees. They're going to be radiating.
So yeah, they definitely do have, but the problem is they're also 10 kilometers in size, so you have to kind of. Right. I'm fairly certain you could. You're basically fine. I once did a calculation that if a human being ended up heated up to the energies of a gamma-ray burst, that we would essentially outshine most stars. So yes, these things are good.
I think I'll take a pass on that one.
Yeah, don't do it. You can
Knock me out on that experiment.
It's a Doctor Who thing.
Yeah, so I imagine that there would be visible light, but exactly what the spectrum would look like is something I'm not quite certain of.
Well, what are these planets made of, do you think? I mean, you talk about them. I mean, what kind of, is it all these?
The formation scenario for these is different than the formation scenario for this planet. This planet was formed essentially out of a white dwarf.
Mm-hmm.
These planets were formed out of the basically segregation of a disk, and the material that's in the disk is basically the same stuff we assume that's in like the sun, which is how you get meteors and asteroids. So we assume that these are going to be like rocky little worlds, very much the same as any that you might find in our solar system, just formed in a slightly different fashion.
And fluorescing.
And and bathed in X-rays.
Hard place.
So what is your research now? What are you kind of like?
My interest has been mostly in trying to explore what the connection is, and I alluded to this mystery, between this sort of system and the isolated systems. How is it that you move from having a system where you have a companion that's very close by, that might be being disrupted but seems to be relatively stable, to just having a single neutron star. And that's what I've been mostly focused on lately.
Wow.
Yeah, really interesting.
So when you come back, what do you want to talk about next
Yeah.
time?
I'm open to suggestions. I have lots of different.
How about the meaning of life?
Yes.
Yeah.
It's not just 42 anymore.
I did give a talk not too long ago about this idea that the Milky Way was a quasar. in the past. So I'm happy to do that one as well.
That was certainly interesting. It got us pretty interested. And I want to know more about the Fermi Bubble too, because that's such because it's such a crazy thing that I've never heard of it before.
Okay, yeah, well that would be a good. There's actually a whole slew of people that get interested in this. There's evidence from multiple lines that this is actually what has occurred from things that are very, very far. Like pure Fermi bubbles are enormous. They just spread way out of the galaxy. And then there's made of ionized gas, essentially. Yeah. And now there's also evidence very, very near the center of the supermassive black hole as well. There are people that study what if you had an AGN and then it sent out shock waves 6 million years ago, how far do they get out? And it's not particularly far, so you should be able to see that evidence as well, and people look at that.
Well, I assume that with Fermi bubbles, though, they couldn't be traveling quite at the speed of light, so we could really wind back time to see exactly when that was, see how far they got, to know when that shock wave was.
Essentially, they have their shock wave models and reverse them.
If it's there, it's, we'll call it 10,000 light years in size, roughly.
Yeah, tens of thousands.
Tens of thousands. It's not.
Well, Milky Way is what, 150,000 light years?
So you're talking tens of thousands of light years, probably 50,000 light
Yeah.
years.
Still crazy huge.
You can see it. It's actually, this is not the best. I showed you not a very good picture of them. I don't know if you can see them. I can see them because I know what I'm looking for, but here's one down here.
What is it?
No, we can see it.
That's great. I'm glad that you did, because not everyone.
No, it's bigger on the top one, isn't it? It looks
I
like
see that big
one
ball.
It's layered up there.
Yeah, but I think it's actually this thing.
It's the
Right,
one on
the inner
inside.
one.
Okay.
It's the inner one. The outer one is one of these radial loops. That's a northern radial.
bottom one.
Yeah.
That's a great picture.
It's beautiful. Yeah, Fermi is just. I'm always amazed by Fermi.
Is there any, when you see, like, humans' eyes are always drawn to patterns, but when I see up at the top, like in the North Pole up there seems to be a cluster of more events that are kind of happening up there. That is just as random could be, though, I suppose. Right?
I think so. I've not heard of any particular reason that there would be clusters like this. Also, the projection, it really doesn't like this picture. The projection of this is skewed as you get closer to the poles as well.
Right.
So I'm not quite sure if there's, you can reproject it and see if that still shows up. There are interesting patterns in pulsar distributions that I haven't quite looked into as much as I'd like, but we now have planetarium capabilities of being able to fly through a lot of these things. That's really fun to do.
Yeah.
So at City College, we sometimes do that. You set them up and you can fly around and see if you can see any patterns.
Well, let Carter Emmert loose on this stuff. It'll just,
I use his software to do that.
Very good. Thank you.
Well, thank you.
Thank you.